Okay, this is the MA205 Logistics Growth block of instruction. We're going to talk about how to model and solve situations involving the population growth using logistics equation. So anything that grows tends to have a limit. So if it's fish in a lake, eventually the fish will run out of resources, in which case they can't grow any further. So they'll reach what's called the carrying capacity of the lake. Or if a rumor spreads throughout a population, say the Corps of Cadets, eventually the rumor reaches all the cadets and it can't spread any further. So these are situations where growth occurs, but then it has a limit, which we're going to refer to as our carrying capacity. So we'll talk about long-term behavior with this model, identify some equilibrium solutions. Okay, so the logistics differential equation looks like this, where this is the change in population over time. Okay, so P is just one case where we'll talk about population. And so this differential equation, this is my proportionality constant, which tells me how quickly something grows or decays. So in this case, usually this number will be very small, and it's all dependent on your time interval. This is our population, and then this is the term that limits my growth. This is my carrying capacity. Okay, so P was population, K was my proportionality constant. So I have 1 minus the population divided by my carrying capacity. So in your textbook, this is just denoted as a capital K, and this is a lowercase k. But for my notation, I just call it a circle K to differentiate between the two Ks. Sometimes your lowercase and your uppercase K will look the same. Okay, so I call it circle K to my carrying capacity, and P naught is going to be my initial population. Okay, so this term will limit how much I grow. If population exceeds the carrying capacity, say this was 2,000 over 1,000, then it's going to be 1 minus 2, and this whole term will result in a negative number, which will make a negative rate of change or negative growth. Okay. So far we've been solving these problems with separation of variables, so you can refer to your textbook on page 594 for a proof of how to separate variables of the logistics model. Okay, you're not expected to know that for this course, but once you separate, if you have this exact differential equation every single time, it will result in this as your particular solution, okay, or your exact analytic solution, where you have the carrying capacity divided by 1 plus a e to the negative kt, where a is the carrying capacity minus initial condition divided by the initial condition. Okay, so what I'm going to do is I'm going to continue this island example where we had the sickness that was spreading, where we had a carrying capacity of 1,000, my proportionality constant 0.03, and my initial condition was 50. So I write out my differential equation, okay, based on this model. This models the growth of that sickness throughout the island. I want to define my variables. P of t is going to be the number of infected people at any time. Time is in days, and the initial condition is 50. So I want to answer the same question I did before, find the number of people infected after 300 days. And I want an additional question. I want to say, what's the time until 900 people are infected? And then I want to talk about the equilibrium values. Okay, so the first thing I can do is, once I know that the problem fits the logistics model, then I can go right to my particular solution and start calculating these values. In which case, A is going to be 1,000 minus 50 divided by 50, which comes out to 19. Therefore, my particular solution is 1,000 divided by 1 plus 19 e to the negative 0.03 t. Okay, it's that easy. That's my particular solution. So now I'm ready to answer my question. What is the population at 300 days? So I want to know the population at 300 days. In which case I'm just going to put 300 into my particular solution. And P of 300 equals 997.6607 people. Okay, the next thing I want to do is solve for the time it takes, the time until 900 people are infected. Okay, so this time I know the answer to my particular solution. This term P of t is going to become my 900. So I want 900, and I set that equal to my particular solution. This is my number of people infected, and I want to solve for this, solve for time. So I'm going to do this in one massive algebraic step. The first thing I'm going to do is I'm going to swap these two terms. Okay, so I'm going to have 1,000 divided by the 900. Okay, so now imagine that this term is now over here, in which case I'm looking at this and I want to move the 1 to the other side of the equation. So I'm going to subtract 1. Now I'm down to this term. I want to get rid of the 19, so I divide both sides by 19. And now I'm left with e, so I'm going to take the natural log of both sides to cancel the e. And now I'm left with negative 0.03t. So I'm going to divide the whole thing by negative 0.03, and that equals time. So my time is 171.39 days until 900 people are infected. Okay, so let's talk a little bit about how this differential equation behaves and the equilibrium values. And I set it equal to 0. There should be no rate of change, so the change in population over time. So if I want no rate of change, I want to set that equal to 0, in which case for this example, I'll have 0 rate of change when the population is 0 or at 1,000. Okay, so if I put 1,000 over 1,000, this becomes 1 minus 1. This term goes to 0, and I have 0 times the population. So that will result in no change. Okay, so those are my two equilibrium values for this problem. If I have the rate of change dp dt is greater than 0, then I have positive growth. In this case, that occurs between when population p is greater than 0 but less than 1,000. And when I have negative growth, the rate of change is less than 0. That's what I get, negative growth. And that occurs when the population exceeds the carrying capacity of 1,000. Okay, now I'm going to compare my answers from my exact solution to my approximation with Euler's code. So you see here I have the same setup from the Euler's demo, 0.03 my proportionality constant, my carrying capacity, my initial population, and I carry out these iterations with a very small step size to get a very good approximation. And you see it approximates this S-curve where the initial growth is very quick, okay, nearly exponential in the beginning, and then it reaches a almost like an inflection point and the rate of growth starts to slowly decrease as you get closer and closer to the carrying capacity, and then it will not go over the carrying capacity of 1,000. Okay, so the first question we had was find the number of people infected after 300 days. So I follow my time down until 300. Okay, so notice here there's a jump from row 17 to row 30,005. And when I get to time equals 300, I have 997.66175 compared to my analytic exact answer of 997.6607. Okay, so my next question was find the time until I reach 900 people infected. So what I'm going to do is I'm going to scroll up until I reach 900 people in my population column. Okay, and here I reach 900, but there is not exactly 900 people, so I'm highlighting both of those cells, and that occurs somewhere between 171.39 and 171.4, and our analytic solution was 171.39 using our particular solution. So extremely accurate with a very small step size that confirms our work.